Okay, I failed to set up my speaker notes so that I can see them, but let's do it anyway. I think it will work. So, fractals on the GPU. It's what I'm going to talk about, and it's two parts. One is slightly bit of math, all math that you need to in order to render nice-looking Julia fractals, and the other part is graphics ecosystem in C++, in particular cross-platform graphics ecosystem in C++. Right. So, why fractals? Well, it's a very simple algorithm. You run a very simple function for each pixel, and then you get a nice result, and it looks good, of course. And it's also it has a nice property because it's a class of algorithm when you can utilize your GPU to the maximum. You can actually get all the floating point operations per second that the vendor says it has, which is not true for like many other algorithms. Anyway, it's mathematically interesting, of course. Okay, so this is almost, this is more than half the code I have in the whole presentation. And the code is roughly what you need to do in order to generate the picture on the left. So this is basically what you run for each pixel in order to get this black and white drawing. Okay, first you define a function f that takes a complex number z and squares it and adds c. And c is a small constant complex number. And if you change c a little bit, then you will change the image a little bit. So fixed c gives you, or fixed function gives you a fixed image, which you then can zoom into and move around in. But if you change it a little bit, then you will well, get a different one. Right, and then the color function is what you run on each pixel. Basically, you have a loop. You translate your pixel coordinate into a complex number, and then you iterate this f function over and over again. And if at some point you see a large number, then it's black. But if all of the numbers stay small, then it's white, and that way you get this image. So very simple. Okay, math slide. I'm skipping that one. Okay, how about colors? Well, to the colors, you also take into account how many iterations your number survived until it grew large. So in the old version, the one to the right, we as soon as we found a large number in the sequence of f of the starting complex pixel value, then it was black. But now instead we convert the iteration number to a color. So suppose you have a color palette, and then you divide, you take like 50 different values from the color palette, and you pick the one that is at the iteration number. And then that way you get like this thing. Okay, so since I don't have that much time, I will not go into how you make smooth colors, but it's like you can almost guess it from this code, because like this code, it has 50 discrete iteration values, but if you instead make them continuous, then you can plug them in to your color mapping and get smooth colors. And there is a clever trick for that. Well, this example over here, it has big problems if you try to zoom deep enough. You don't have to zoom pretty far until you see floating point artifacts. But there is a really cool trick, really cool mathematical trick that, and it works like that you take one complex number, then you calculate the sequence with very high precision, like 256-bit floating points, and then you base the other ones on that, and you do some math. and that way you can zoom and zoom and zoom and zoom. But like if I get to the demo part, then you will see that it's pretty fast. You run out of load precision. Okay, so now to the second part. Different graphics frameworks. So I started doing this. I started writing a prototype that used CUDA and OpenGL. But then I wanted to do something a bit more cross-platform. I wanted to do something that I can develop on the laptop. And I searched for different frameworks, and Vulkan sounded like a good idea at first, until I watched a presentation, and they suggested that, well, you should at least read these books in order to get into this. And then I thought that I will try something simpler first. And then I found WebGPU. And WebGPU is it is a JavaScript specification for a JavaScript API, which is available in most browsers. And there are two implementations of that. Google has developed Dawn, which is part of Chrome, and Mozilla has developed WGPU, which is part of Firefox. And both of those implementations, you can basically use them interchangeably. They come with a C header, and you can make them emit a library that you can then link to. So I tried Dawn. I think I have a build script that I think it actually should work with WGPU as well, but I haven't not tried. Okay, so here is the reason why I did not choose Vulkan. So instead of hello world in the graphics world, you have a hello triangle. What code do you need to write in order to just make a triangle on screen? And well, in the good old days, for 25 years ago, when OpenGL was new, the hardware was simpler and the software was simple. There was a function like draw triangle, and it drew a triangle, and it had basically hardware implementations. But then, as the hardware developed, the software also got more and more complex. Vulkan seems to be in the lead, or at least tied with DirectX 12, if you count the number of rows. But Vulkan continues, and continues, and continues. Apparently this is a bit like cheating, because this Vulkan example has more error checking than the others have. But still, and you need to do all that in order to like just make a triangle, and I have a bit more complicated things than triangles. Okay, so now to a very short introduction to WebGPU. WebGPU and basically other graphical frameworks, they have the concept of shaders, typically small functions that run on your graphical accelerator. And in WebGPU, they have a language called WGSL, WebGL shader language, which looks very much like Rust. And this one is this is an old version. There is a bug. It does not compute the imaginary part. Anyhow, it looks like this, except for that it's a bug. Well, everything is typed. You have only a few data types. You don't have 64-bit floats. You only have 32-bit floats, for instance. And this is basically like the more or less almost working version of the loop that you saw before that computed colors. But this one only computes situation numbers. Right. Okay. Also worked. Okay. Right. I have. This is an old version of the slides. Sorry for that. I forgot the slide that with like, overall learnings and recommendations. So I'll just make something up. So well, I spent a few weeks across a few months in learning how to do cross-platform graphics programming. And well, my learnings was that I really should not have picked Dawn and C++ because there is, it's not very popular. It's very difficult to build. Okay, someone in the audience disagrees, but it doesn't. I mean, the Rust version seems to be much more like much more hobbyists just take the WGPU crate and work with that compared to the Google library. And I really should have started with doing it in JavaScript in the browser instead of doing all this. So like in the end, the demo, which I have not shown yet, is, well, I mean, it's 3,000 lines of code, and most of it is setting things up. The actual logic is pretty simple. So yeah, you should really think how much you gain from from having a complicated cross-platform library, and also there is already a very good cross-platform graphical library, and that comes in the browser. So like use that together with or some browser-like environment like React Native or Electron. Yeah, and finally, also something that also was missing from my slide is that today I wanted to make a benchmark and compare like how fast is this compared to like using unoptimized JavaScript and computing one pixel one by one in the browser. So I asked the AI, write me a website that does that, and I figure out that it's, I mean, we don't win that much. Like I do roughly half a millisecond per frame. JavaScript does maybe 50 milliseconds per frame. Unoptimized JavaScript in the browser.
Did you check the code coming out of the AI? Make sure it's unoptimized and...
Yeah. I looked at it. Yes, I have it in the right version of the slides. I can show you later. Okay, let's see if I can get a demo running. How are we on time? Okay. Let's see. Julia GPU. Do we have a build folder here somewhere? Yes, we do. Red screen. Okay. No, wait. It actually did work. If I made it full screen. Okay, so here it is. It works. You can drag it around. You can zoom into it. Fractals are really nice looking, in my opinion. Yeah, and I want to zoom in so that you can see the floating point artifacts. Here they are. And we can change, can try to change the number of, okay, so here the sun is rising or setting maybe. This is the effect of changing the maximum number of iterations, which was 50 in the slides. Right, my presentation also did not have an end slide, but this is the end. Thank you.